Hello, Stratus, are you there?
So,
Can we
hello.
begin?
Yeah, sure. I think it's time. So,
Yes.
can you hear me, everyone? Hello from my side. My name is Roberto, and today we're going to drive the upcoming first webinar series for young engineering geologists. I'm pleased to introduce our first speakers, Dr. Vassilis Marinos and Dr. Louise Vick. Professor Marinos is an associate professor in the Department of Geology in the Laboratory of Engineering Geology. And Dr. Louise Vick is a research fellow from the Arctic University of Norway, specializing in rockfall and rock slides. Before I hand the mic to Professor Marinos, I have a few housekeeping items to cover about this webinar series. First, today's webinar will be available online via YouTube, official e-YEG channel. And I would like to encourage you to follow the webinar's guidelines to mute your microphones and turn off your camera. We'd love to hear from you after each presentation. There's gonna be a 15 minutes space for questions and answers from the presenters. So you can provide the questions right after they finished in the chat chapter. So last but not least, I think everyone can share this information is really valuable for everyone. So without any further ado, I'd like to kick things off by welcome e-YEG Vice President Vassilis Marinos. Vassilis, the place is yours.
Let me share my presentation. So hello, everybody. Can you just please verify that you can see my screen?
I think everyone is
Everyone,
okay.
Is it working? Okay, that's great.
Yeah.
So first of all, as an engineering geologist, but also as the vice president, one of the vice presidents for Europe of the International Society of Engineering Geology, Association of Engineering Geology and the Environment. This is a very great initiative, and we are very happy that the e-YEG has started these seminars, and maybe it was a very good opportunity after all this crisis that we are living. But in any case, I believe that this would be something that will continue, and congratulations to you all that you said this. My title of the presentation is quite general. I understand that. It's rock slopes characterization. So I will try to be the senior of the group and put some more general states and maybe give the fundamentals and some background. And so I will pose the questions, and then I will speak about isotropic failures and anisotropic failures. So this will be mainly, this will be very fast because I don't want to be a lecture. And then I will focus on how we can put the geological focus on rock slope characterization. And then we'll highlight this through some case studies. Of course, I will end with the conclusions. So which are the questions? Our scope, our responsibility as engineering geologists. So how is the ground? We need to compose a ground profile and to give the engineering geological model. The second one is how the ground works. Find the critical failure mechanism and define all the characteristic engineering geological keys that configure this behavior. And the third one is which are the critical design parameters to assign to the analytical numerical model. If we'll see this very well-known Berlin triangle, we engineers follow, you can see these three basic areas of activity that encapsulate the practice of geotechnical engineer. And we are entering into this triangle as engineering geologists and try to contribute through the ground profile by an understanding of the geological genesis and evolution, and into predicting the ground behavior, and then to the idealization process where an appropriate model is designed. So we have to ensure that the reality is modeled. You can see a rock slope characterization can be, of course, according to the rock mass type, and we will focus there. But also, we should take care about the scale of the problem. So according to the lithology, taxonism, weathering, alteration, and the geological history of the material, the sliding material, history of the material, we can have an overall problem of very big slope, but also we can have a smaller, smaller scale problems that we can see in the same geological environment. But when you see, for example, in this open pit mine, when you want to assess the stability of the bends of this open pit, then you may have, for example, a structurally controlled failure guided by one plane or two planes, providing anisotropical failures. But when you see the in another scale the problem of all the benches of hundreds of dozens of meters or hundreds of meters, then you may have problem of isotropical failure. You can see this is very nice pictures, bend scale slopes in a very well-known open pit. So you can see in the bend scale the problem more structurally oriented, and the joint strength parameters are of greater importance. But when you see that in a 500 meters high slope, then you can see the rock mass as homogeneous. So you can treat it as a rock mass problem than a rock joint problem. So we have this distinct case of on the left an isotropic failure, on the right an anisotropic failure. In the one on the left side, we have to focus on the rock mass properties. On the right side, we have to focus on these persistent predefined discontinuities, their geometry and their shear strength properties. And then, of course, go and select the most appropriate failure criteria. I give here some examples. So here, for example, these pictures, you can see we may have a very folded, highly folded area from the Greek mountains. Here, the overall failure will not be guided by the rock mass anisotropy, though we have a lot of bedding planes, but you can see how these change their directions. So an overall stability is guided by the rock mass parameters. And on the other hand, on this slope, the rock joint properties are mainly required. So our first question before going and assessing everything in the rock slope is how does the ground work? In any case, we can use whatever we want of technology, modern technology and computing, but first we have to go back into our material and answer how is the ground and how the ground works. So in general, we can distinct, let's say, our rock in this very well-known fabric types of rock masses from Hook, introduced in 1994. I'm not gonna give details about that because, as I told you, this is not a lecture, but you can, if you haven't seen that, you can see that from intact rock, from to blocky, very blocky, disturbed, to brecciated, and laminated, foliated, sheared, we can have from highly anisotropic failure, then to reasonably isotropic. And of course, this has to do with the site-specific particularities always. And this is one very generalized table, but this is just to give an idea how to think the rock mass type with the anisotropical or isotropical failure mode. So the rock mass type that we're discussing, if we want to go back, not just see these small pictures, very well known of the structure of the rock mass, the genesis, of course, is reflected on the quality of the intact rock and the inherent structure. So it's very, very important to focus there. The tectonic evolution also reflects on the rock mass structure, the fabric, and of course the quality of the joints. And then the paleogeographic evolution to the weathering, the alteration sometimes, and final fabric. So if we want to categorize the definition of rock mass types, we can detect the strength and deformability of the intact rock. Here in the slope, we mainly focus on the strength. And quality of the rock mass is the second category, the structure, the strength of the rock mass, and of course, the joint properties as the third category. So intact rock mass and joints. So let's go to the isotropic failures, the rock mass parameters. So in general, as you may know, if we don't discussing about a very recent, not fractured rock, which is intact, and we may be able to measure it in the laboratory. But if this is not a case, then it's very, very difficult to measure as far as the scale is concerned in laboratory, as you most of you know. In situ testing, we have a problem of the scale, we have a problem of the time, we have the problem of the cost to cover an assessment in the rock mass properties. Of course, back analysis is our best approach into finding the rock mass parameters, but on the other hand, we have to have failures. So we have to wait and have a failure, or we can take advantage of how the ground works in the neighbor of our problem and try to take advantage of that. The correlation with the rock mass classification of these rock mass properties by using a GSI, by using an RMR, by using Q or other rock mass classification problems is it is a very competent tool into assessing the rock mass parameters. The RMR and Q classification systems are also used, although were not established for this purpose, but for giving recommendation for the support design in tunnels. Of course, the SMR was also introduced for the slope stability assessment. But bear in mind that now we have the development of extremely powerful microcomputers and of user-friendly software. So we have a higher demand for reliable input data related to the rock mass properties. Again, if our rock mass behaves isotropically. So if you want to put that into numerical analysis in this kind of failure mode, then the geological strength index, the GSI, is such a classification. So it's a key to achieving effective rock engineering design. And we can use it in the Hook and Brown failure criteria. You can see that there's equation, very well known. And you can see in these transition equations that our unknowns are a uniaxial compressive strength of the intact rock, the constant MI, and the GSI. This is the numerical idea of the isotropic rock mass for analysis. Of course, we have also the disturbance factor into the equations. That is very, very important also for the slope stability assessment. So the GSI can be estimated by this chart, they generalized this Hook and Marinos 2000 chart, and you can see all the structures in the lines and the surface conditions of the joints in the columns. So you see from the cores, from the outcrops, you see your rock mass, and you try to find the structure and you assess the joint qualities. Of course, you can use the quantified charts, either the Hook et al. 2013 or others in the literature. There are many of them, but mainly our work for the blocky, very blocky structures, not for the very weak rock masses and complex and heterogeneous. So the Hook and Brown parameters for, you can see here in this these ranges, these combinations in this diagram. In the x-axis, you can see the uniaxial compressive strength from 10 to 300 megapascals. And on the x-axis, you can see the constant MI. And you can see the different GSI charts working for the ophiolites, working for the gneiss, granites, for the fleece formations, for other sedimental formations. You can see all these bubbles inside these numbers are different geological combinations of in relation to tectonism, in relation to weathering, in relation to alteration. And we will focus about that later on. But you can see our challenges in order to find where we can be in this chart. So we have great combinations. Also within the same rock, I know that a lot of you for designing, you may follow tables or in the literature to see in your rocks the range, and you can take some numbers. But in this chart, you can see for recent publication in rock mechanics and rock engineering that this varies a lot in both parameters of the index rock. So you should take care when you take this, and it is better always to perform your own laboratory test. So once GSI has been selected, the system becomes highly quantitative, and GSI can be used as input into numerical analysis or closed form solutions. There is no intention of replacement of the other systems because it has no rock mass reinforcement. Its only function is the estimation of the rock mass properties. So let's go to the other category, the anisotropic failures. Of course, most of you know this. This is a straightforward analysis. So where we have predefined with a very large continuation within the rock, then we may have these anisotropic failures, so planar sliding, wedge sliding, and the analysis is pretty much straightforward. You all have seen these very nice slides and how we assess this. And our analysis, of course, is into taking all the geometrical features of these joints, not only the dip and dip direction, but also the distance, also the persistence. This is very, very important in order to model the reality, in order to model and calculate the factors of safety into the real block volume and not what the programs by default gives you. And of course, the shear strength properties of all these joints, so roughness, weathering, wall strength, opening, all these you are very well known. And we have in our, as a tool, very, very rapidly growing in all the young engineering geology group, these point clouds and how we process them from UAVs or from LiDAR technologies, and we can have immediately and very, very fast a lot of measurements and in very difficult slopes to assess. And we can have these geometries in steep and high slopes, and by not using our compass, of course, also always we should validate them, and then we can have the joint spacing or the block volume assessed with these tools. And then, of course, then going perform our kinematic analysis by using this data coming from this computing. Of course, then we have to assess our strength of the joints. So either we can obtain some shear tests in some natural joints, or we can perform in artificial joints and then obtain from the failure criteria. They are in the literature. Here you can see Barton and these very well known, and by taking the JRC, the JCS of our joints, then we can assess the shear strength of our joints. So we can identify and measure the orientation of the major discontinuities and the calculation of the shear strength of the joints, the determination of all the possible potential wedges and then calculation of the factor of safety, then assessment of the appropriate support measures. So this is a straightforward, now we can do it maybe faster and maybe in much more detail with our 3D point clouds. But again, you have to be realistically about the geological information, about the water presence, about the joint persistence and the joint spacing in order to model the rock block size and the factor of safety, and of course the stresses. This is our very good, let's say, contribution in this analysis, that we had to do it in less time. Now we can do it faster if we can understand, of course, how the ground works again. So let's now step into how we can put in the geological focus on the rock slope characterization. So how tectonism reflects on rock mass characterization and slope behavior, how weathering and how alteration reflects on rock mass characterization and slope behavior. Of course, indeed, you must provide the model for the analysis, provide the numbers for the analysis, but do not forget, always focus back to geology and ask yourself, how is the ground and how the ground works? So provide a more realistic model and provide the appropriate numerical analysis based on the failure mode and provide the appropriate design parameters. So the computer cannot do your job. It can help you do it faster. It can help you do it in an, it can help you to be very much detailed into that. But you never, you shouldn't forget your background. So how tectonism reflects on the rock mass characterization and slope behavior. So from low to moderate to severe, you can see how this reflects to the slope behavior. So for example, here we have degradation due to shearing and fissuring. This is a fleece formation. On your left side, you have a moderately disturbed rock mass with sandstone and siltstone alternations in similar amounts. And on the right side, we have the same formation, but in the tectonic zone. So this is tectonically disturbed sheared siltstone with broken deformed sandstone layers that almost form a chaotic structure. Again, some very nice pictures of this fleece. And you can understand by in the left side, that is highly anisotropical, its behavior, depending, of course, on the geometry of these joints. And on the right side, you see a shear zone influenced by tectonic thrust. And here it is a behavior reasonably isotropic. So the rock mass parameters is our main focus. So for example, here in the fleece, we have alternations of something competent and something incompetent, which is highly tectonized, very often highly tectonized, because it is connected with the alpine chains. So we have a lot of folding, we have a heavily shearing, we have a degradation due to this shearing and fissuring, not only to the structure, but in many cases also in the intact rock scale. And we have the presence of clay formations that, as you understand, highly can give you easily these rotational slides or smaller slides within your slope. And weathering of the silty clay members that are susceptible to slaking. Also, the groundwater downgrades the quality of the silty clay members and induce poor water pressures. And the profound bedding thickness variety also plays a fundamental role. So we can characterize a fleece by this chart, and you can see we have 11 types of fleece depending of how what prevails: sandstone, the good part, or siltstone, the weaker part, and how much disturbed it is due to the tectonism. So you see different types from the first lines, which is undisturbed or moderately disturbed, then going to the right, which the siltstone prevails more, but again, the structure doesn't change, and then going down to the lower floors to this heavily folded but retaining their structure rock masses. Here, disintegrated rock masses, In the first case, we have a lot of sandstone, but in this nice picture, we have more the weaker, more ductile material of shales, of siltstones. And then the blockiness here is lost. We have a foliated, laminated structure. So this is, let's say, the weaker rock mass we can have into this model. Of course, we can use these numbers, we can characterize them, we can assign numbers, but when we use them in an equation of the Cook and Brown, we can use it only for isotropic rock mass behavior. So we can standardize the mechanism of slope failures in these 11 rock mass types, and its behavior is controlled by this heterogeneity, by the tectonic disturbance, by the weathering degree, and of course the groundwater pressures. So we have mainly for structurally controlled slides in types 1, 3, 4, and 5. I understand you don't remember what are these, but I will show you in the next table. So we have potential kinematic favorable conditions here as a controlling factor, and the shear strength properties also. The bedding planes are the more essential discontinuities because they persist in space, but also other joints because we are in a fleece environment, so they also continue in space. They are somehow a little bit not continuous because we have these alternations of something which is more brittle, it's a sandstone, and something that is more ductile. So they do not continue, they don't have the same deformational characteristics, so they don't continue very large lengths. Of course, we have biplanar slides in a combination of weak persistent joints. Here you can see the different rock mass types from type 1, 2, 3, and 4. You can see the principal failure mechanism and the engineered geological factors. Since our presentation, it is recorded on YouTube, I'm not going to stay here. And of course, this is not very friendly, but just to give you an example of type 3, you can see here the model disturbed sandstone with thin intercalations of siltstone, of course, anisotropical behavior, and which is our characteristics that we should focus in our site investigation, in our assessment in the field and in the laboratory also. And the rotational landslides are mainly in types 6 to 11, and the controlling factors, of course, lie here in the rock mass strength. So in the later case, the Cook and Brown failure criteria and the GSI values can be applied here for slope stability analysis. So you see here this kind of types, type 6 to type 7. And again, the next table here from 8 to 11, here we have a highly tectonically deformed, intestinally folded and folded siltstone or clay shales with broken tooths of sandstone. They try to follow this plastic deformation. So they contribute not too much, but this is not a completely chaotic structure. So we have a reduced shear strength of the rock mass due to the tectonic disturbance. Here the intact rock strength is very, very low due to this shearing, and the water presence reduces significantly the effective stresses. And we may have some possible water in sandstone blocks trapped within this impermeable mass. The weathering degree, of course, it's of higher importance here, and the presence of clay minerals, again, it's very, very important in our assessment. So let's go now to weathering. Here, how weathering can affect. Of course, in our slopes, weathering, it's, let's say, a primary focus on where does the weathering stop. But there are some environments where weathering may not stop in the few meters, so it can continue in depth. So we may have some, for example, here in gneiss environment, some sound gneiss from, of course, evidently very competent rock mass with minor problems in geotechnical works. So mainly, let's say, structurally controlled problems. But when these are heavily tectonized and weathered due to this tectonism and also due to meteorism in tropical or semi-tropical environments, then you may have a weathering degree that continues in depths. And of course, we in this environment, we have to be very, very careful about this presence of shear zones in depth, where weathered is favored. So you can see, excuse me, this GSI and intact strength change from weathering grade according to ISRM definition grades, and you can see from fresh to residual soil, or from residual soil to fresh. Of course, from the top to the bottom, we may meet in the top, in our surface, these rock masses. And you can see how the intact rock strength can be reduced, and also how the structure can be reduced in this table. So this is very, very important for the rock mass characterization in a weathering environment. And you can see this chart published in Geological in 2018 of how this basically this basic chart of GSI it is being calibrated and substitute the straight lines by the curved lines, bended to the left side of the chart. So as weathering degree here increases, bending is increased as well. So the chart maintains the basic structures, but the surface conditions, the columns here, are replaced by the weathering grades. So again, different kinds of gneiss, depending on how much weather it is and how this foliated structure is intensive, we can have different rock mass characteristics, and we can have different behavior. So just to give you some zooming in some cases, and in one we may have presence of several circular slides and a few planar wet slides and small blocks. This is a type 4 moderately weathered gneissic rock mass. So this is natural in gneiss. New clay surface zones, and the intact rock strength significantly is reduced, etc. So you can read it by yourself. But these gneissic bands still are the principal joint surface. On the other hand, then we have a heavily weathered rock mass. Then the rock mass has faintly retained its structure, and we have a circular or multi-surface failures. And here, the discontinuities are not clearly defined with certain geometrical characteristics. So our focus here is on specific shear zones or in our overall rock mass strength properties. And you see here, for example, this is a heavily weathered zone. So our focus in the South investigation programs by borehole is to identify this weathering profile and how it continues in depth, but also along the slope in order to model it. And in these cases, we can use a back analysis in order to obtain the rock mass properties in this shear strength, in these shear zones. So you see one example here published in this kind of rocks. Also, we may have these multiplane failures when we have this very good and maybe slightly or moderately weathered gneiss, excuse me, but all these can be can fail if we have shear zones within this environment. These shear zones can be subvertical, can be sub-horizontal. You can see in this kind of example, and so the good gneiss can slide along these surfaces. So we should search in our geological history and the tectonics in the area and map very, very well these zones, which we may not see them on surface by all our very good tools we have from LiDAR or from UV. So we have to go back into here, help with a traditional geology and site investigation program. But we need to know what we are searching for. So this is very, very important. And finally, the alteration and how this alteration reflects on the rock mass characterization and slope behavior. So for example, in a phylitic sequence where we have a sequence of mafic, basic and ultramafic, ultrabasic rocks, we may have geometry which is highly disturbed due to this history of the Olithic complexes, occur mainly in tectonic zones, with superposition of numerous overthrusts. And these overthrusts are very much helped by the serpentinization that happens during the crystallization of magma. So you have this transformation of these ferromagnesian minerals, olivine in particular, to serpentine. And this can happen anywhere within your mountain, not just close to the surface. So you may have some very deep zones of serpentinization, which are very weak because our new minerals are softer than the originally compact ones. So we may have some surfaces which are in depth, and this geometry can favor a lot of slope instabilities. So we can start from very good competent periodites, but then we can go down and right due to this serpentinization to weaker rock mass, softer surfaces, but then not just stay this serpentinization along the surfaces, but continue into the intact rock, but also to the rock mass structure. So this serpentinization can affect the intact rock, as you can see, from the 100 and 200 megapascals, and can shift to 5 and to 20 megapascals. And this can be done very rapidly along your problem, along your slope. So, of course, you may have, as you can see on the top left, structurally controlled problems, but when you're gonna meet within this slope, for example, specific surfaces that are highly serpentinized, maybe foliated, maybe clay zones present, we may have an overall stability problem. Of course, falling blocks along the cut can be easily be done along the very soft serpentinized zones, but also we may have, as you can see in this very nice picture, you can see the suspicious amphitheatrical shape morphology. We can have a larger instability of the overall slope problem. So this is a rock mass problem if we have to see the overall stability. And then when you are talking about not just a slope scale problem, but maybe the whole slope, the mountain scale problem, then you have to do huge earthworks in order to stabilize that. So let's go to some case studies. Here we have a Trans-Adriatic pipeline route. It is a natural gas pipeline that runs, let's see that behind, excuse me, from Caspian Sea and transmit a natural gas pipeline to Europe, crosses Georgia, Turkey, and of course starts from Azerbaijan and then to Greece, Albania, and goes below the sea to Italy. Our main problems were within this environment here, and it is a fleece environment. You can see many routes we try to find. You can see in these polygons a lot of landslides in this area. So we try to map along the route, to characterize along the route the rock mass, and you can see the different colors here are different rock mass types, are different fleece types. According to the GSI, these were evaluated in order to perform slope stability analysis under the seismic ground acceleration and under the pore pressures that are expected during the life of the project. And you can see here the huge landslides that the pipeline has to face, of course, had to avoid because this could not be treated, this mountainscape landslide. So we characterized all these 82 landslides in this, let's say 60 kilometers per problem, and try to assess its behavior in relation to the pipeline, and if it's going to reach the crest of the pipeline. Here already the crest of our landslide rates are reached. So we performed some boreholes in order to see in some pilot cases how deep are these landslides. You can see this sliding material in the top boreholes. And in the right, the bottom side, you can see the non-slided material, of course fractured, but non-slided. And you can see the shear zone where the sliding is occurring on the bottom left side. So we assigned the GSIs and we performed some numerical analysis by characterizing these materials, and then had to answer for these 82 landslides if all these could threaten the pipeline integrity. And in order to do that, I'm not staying here a lot because you can find it in the paper I'm writing in the bottom. Based on the landslide area, the depth, the proximity of the pipeline, the activity and the ground quality, the slope angle, and the landslide interaction with the pipeline, then we have to do that ad hoc. So we cannot use any previous classifications. So we have to walk along them, we have to find them, and we have to understand how the ground works. So in order to answer all these questions that are posed to the geohazard expert, you can see that in these slides, we have to understand very well in our site-specific geological particularities, how is the ground and how the ground works, and what is the interaction with the pipeline. The next case is a Roberto landslide. This is, you can see here the church, which is not in its plates. It's 50 meters below its initial, but it stands in its position, which is extraordinary. And a lot of buildings that have collapsed due to this very large landslide done in the Fleece. So you can see here this Roberto in 2007, in 14, and in 16. And we can see using change detection all these movements within time. And our model, in order to understand why this landslide is happening, you can see this is a very folded fleece formation in the thrust zone with limestones, which are fitting with a lot of screes, a lot of water. So this is a very, we have a very weak zones within this fleece environment with very low GSIs and a lot of water that elevates the groundwater pressures. Our next case is PS landslide in Acheloos River in central Greece. Here you can see by your own these very large numbers, and whoever studied very, very big mountain scales, giant scale landslides, these belong to them. So we have, our problem here is a dam. You see here, this is a right abutment in this case here. And we are seeing, fortunately, let's say fortunately, this giant landslide, it is immediately downstream of this dam. So we have different kind of unstable masses, and we have a limestone, which is a very competent in general rock mass. And you can see here Victor Milligan, and consultant for the public operation hydraulic works in Greece, that he sits in this red line there, which is, let's say, 60 million cubic meters assessed sliding mass, which is a very, very large number. But there is also an appreciation that there is another unstable and another very old scarp upstream here in the slope, which makes up to 200 million cubic meters of sliding mass. And you are thinking how this limestone is sliding. And now this is another picture sitting in these limestones, and we can see the abutment of the Sika Dam, and in the red arrows here, the unstable part of the slope. And you can understand that if we have this sliding mass, even we are downstream of our dam, then we won't have our spillway working, and we will have significant problems in the greater work by far after the same dam, the dam itself, which is a spillway working. And of course, it is the geological history. It is the problem lies on this very big thrust of this limestone upon the fleece formations. So this is the very weak material that the limestone are sliding. And this can remind you of another classic failure, the Vaillon Dam Valley. So it reminds a lot. So the spillway is now on the other side by a tunnel and not by an open cut in order to avoid, in any case, when this sliding will occur, to avoid the problems. This is another example of how we can characterize with by using LiDAR and photogrammetry point clouds. And we can find the GSI or any other rock mass classification systems that is heavily depending on the quantification. So you can see this case. This is in central Greece. This is a very important road going to a monastery. So you can see this is a limestone again. It is a fractured limestone. It is tectonized, but you can see its structure is subvertical. You think that this is a folding, so this is subvertical, then it's folded, but actually this is a fold plane. And when you use these point clouds and these very nice computing programs in order to find the RQD, so the volumetric volume by the different colleagues that has published this work, and this is our own work in defining the GSI by this, you can see that we have a lower values below this white line and higher values below above this white line. But these higher values, it's not because the rock mass is better. It's not because the GSI it is higher. Yes, the point cloud gives you this number, but actually this is the fault. This is the mirror of the fault. So this is heavily structurally controlled failure, of course, and the GSI should not be applied in any case. But I'm talking about the application of these programs, and I wanted to highlight by this example of understanding how is the ground and how the ground works, and not by saying, oh, this is a very nice picture, this is a very nice colors, and this is your GSIs or RMRs or Qs. And also, of course, you can, by recent work by Cardenas and all in remote sensing, you can characterize your rock mass, even if it's a landslide or not, a rockfall or not, by object-based analysis in this case. So this is probably my last, due to my time restriction. I started my first slide by this very nice picture. This is Santorini. This is our cradle of our tourism, let's say, our hot touristic island. You all know that. And this red beach is crowded by tourists, and the environment is of particular beauty. We have very steep and high slopes, but also we need to maintain the aesthetics. This is an archaeological site because there is a very close by, there is an archaeological buried old city. So this is protected by the archaeological the archaeological group. So here our problem is that we have a lot of rock blocks of different size falling. They fall immediately to the beach zone, where we have many unstable ready-to-fall blocks and high rockfall hazard along the whole beach. And this falling rock, scoria, this is the initial rock, it is scoria, so it's a volcanic, this is a very old volcanic rocks. It is red due to the oxidation of the scoria, and all this material, when it falls, you can see how it covers the whole bit by several fragments. You can see by these very old photos we found in the YouTube, in the Google, very old, a very large, excuse me, rockfall. So you see in the left side something which is missing in the right side. And this, since it is colored, we don't know when this happened, but this is definitely some decades ago. And you can see here some other pictures and how this is a slope, which is very, it is recent slope, geologically speaking. And it is, this old volcano is cut in the middle. And we have these very steep slopes, and we have the stress relief of the rock mass due to this inclination and the continuous erosion of the beach. We have the development of tension cracks. So the tension strength, the tensile strength is not very high here. And the nature of the geomaterial, it is highly erodible and fairly cemented in places. Also, we have the lava flows dipping towards the slope. So we also may have, as you can see here, some planar failures. The sea erosions undermine the steep slopes and the discontinuity opening by rain, temperature change, and the air, of course, and some earthquakes we have in the area, mainly coming from the volcanic activity. So we have a continuous evolution of this morphology by episodic characters. So the material cannot maintain in its base, it just to stabilize the problem. It immediately was by the sea. And when I say immediately, I will show you afterwards, it takes just maybe some months to do that. I mean, the larger percentage of it. And so the slope does not balance. And at once we have a new cycle of tension cracks, joint opening, the development of new rockfalls. And here we have this Korea, which is coarse-grained, medium cemented volcanic breccia and thin-grained, well-cemented volcanic breccia in places. And when they fall, they completely lose their cohesion and disintegrate. And the lava flow, it's in beds and plains in places. These beds are not favorable for the stability. The low tensile strength is also of higher importance. Here you can understand we cannot easily use these well-known systems like GSIs, like the RMR or anything else. Of course, it is very, very important to form, as I told you, laboratory specimens in order to perform shear strength, immediate shear strength laboratory tests, because the material disintegrates. So we have to do a back analysis in these cases, or use our literature review and similar materials. So you see here, which is the friction that this material, it's stable in these cases, 35 degrees almost. And we perform some back analysis. Of course, this is not our scope to say about stabilization measures. You can find it in the literature, our work, but in order to maintain the aesthetics and their ecological character, it is not a feasible engineering geological case in order to assess its stability. In order to maintain its environmentally character. So you see, this is a very recent, this is a previous week picture. We can use sequential point clouds in order to assess its behavior, its mechanism, how this works. This is work after 2017. So what you see here in this picture, it is, let's say, the red zones of what is moving. But then going the last week, we saw this is what is red is something that it is compared with last year measurements, what has been destabilized, and you can see in blue the new material that has been in the beach. And this is an older picture comparing the 2000 up to 2018. And you can see in the left side, this material that has fallen, you can see in picture this problem in the northern side of the beach. But when we visited that the last week, so after, let's say, 1.5 years, you see this material now is red, which means this is something that has been washed out. So we can measure its speed of removal, this material, how it's removed from the base of the slope, and of course in detail how these tensile joints are being developed. Again, an OBIA characterization was also done by a recent study in this slope in Red Beach. Yeah, I will try to end my presentation. This is a very fast in Plomari Island, a rockfall, and how we can use some UAV flights in order to try to assess the joint properties. But we have already talked about that, and the spacing, etc. But what I wanted to stay in this example and say it's that we can also use that for a hazard appreciation and put some ratings in different kind of, this is a structurally controlled failure, so the wall strength modification, the spacing, and the persistent, the roughness. So we can assign some numbers. But always when we do that, we have to focus back in engineering geology and how we selected the ratings in this site-specific area according to the rockfall history. So these colors and these tools are very, very useful, but we have to put that in our perspective. So concluding my presentation, let's say that the approaches we apply associated with an appropriate factor of safety based on the degree of uncertainties are satisfactory, provided they are not erroneous. It is then obvious why the geological judgment must be always present and why it is so important. And I'm not feeling at all but by saying this in this crowd of people, because most of you are engineering geologists or you are working with in the geoengineering, so you can understand what I'm saying. But I'm not doing that by any lack. I'm doing that on purpose. So I'm telling you that in my last conclusion. So rock engineers have to work within the limitations of available technology, and some of the most severe limitations are associated with the estimation of the rock mass properties. So the efforts to overcome have resulted in tools like GSI, which can be regarded, of course, as interim solutions. And these efforts has been, in most cases, useful since there are very few practical alternatives available. And indeed, such a form of rock mass characterization like GSI has considerable potential for use in rock engineering, because it permits, sustains, let's say, in a great geological logic, even in extremely heterogeneous and complex geological formations. Of course, when you know when to use it. So I have seen in all my students, in all young people, all their passion in developing all these computing programs and how we use all these powerful computers, softwares, and technologies into in the engineering geology assessment in our rock slope characterization and the assessment of behavior. As a senior in this first webinar is that you shouldn't be carried away only by computer and modern technologies. You will use them and you will grow with engineering geology for sure. But you always have to focus back to your conceptual engineering geological model. And you have to strangle and correlate with the engineering geological particularities. If you don't do that, then you will put aside our work and only the computers will do the job and we won't model the reality. So e-YEGs, this is a great strength to you, but also your responsibility for the future of engineering geology. I thank you very, very much for your attention. And since we are recording this, I want to run down the references for the record. And I would like to welcome you in the 3rd European Regional Conference of e-YEG next September. Of course, I hope that we meet in person. I hope the COVID-19 will allow us to have a wonderful meeting, and I wish to see you all there. Thank you very much.
Thank you, Professor Marinos. Thank you. It was a really informative presentation. We're a little bit over time. I think we have time for a quick question. If someone from the audience should provide a quick question, or okay, we have a question from Renos Christakis. Professor Marinos, question for marginal cases. When a case lies very close to the threshold of isotropic, anisotropic, which path would be safest to adopt? How vague this could be? What are the major factors to consider when deciding in order to derive an appropriate ideal model? I think you can answer the first question, and later on we can start with the next presentation, and you can answer personally.
Okay, so this is a very good question, and this is always case specific. So depending on your site investigation, and either you are marginally, let's say, the one site on the other, you have to perform both analyses, not just either one. So you have to do both of them, and to see, model the factor of safeties, and try to stabilize with both of them, if you think that both mechanisms are possible in your case. So this is what happens in reality also.
Okay, I think more questions should be answered from the chat section. I think we have to move on to our next invited speaker. As I mentioned in the beginning, our e-YEG representative is Louise Vick, a research fellow from the Arctic University of Norway. Sorry, Louise, for taking some of your time. I think most of us find that it was really informative. So, a small brief of Louise is our upcoming e-YEG chair, which served for e-YEG chair since our beginning of our committee. So, Louise, the space is yours.
Thank you, Stratis. And thank you, Vassilis, for providing a really nice platform for my talk, which actually flows on really well from yours. It's almost as though we planned it that way. So I'm very excited now to move from the more applied work that Vassilis has been doing into the realm of the geofantasy, as I talk to you about some large rock slope failures in northern Norway. So I will just share my slideshow. Let's see. Okay, and you can see it, all right?
I think we're okay, yep.
Great. Yes, okay, as Stratis mentioned, I am a researcher at the Arctic University of Tromsø, and I specialize in rock slope failure. So today I'm going to talk to you about rock structure and landslide development in northern Norway. So first I'm going to give a little bit of background to the type of slopes that I am talking about. And then I'm going to talk about the relevance of structure and considering structure in slope hazard analysis. And then I'm going to give you some nice examples from northern Norway and talk you through how we have categorized them as part of this study. So the slopes that I'm talking about, we commonly refer to them as rock slope deformations, because we see deformation at the surface, but we don't always know what is happening at the subsurface. So these are very big mountains rock slopes that show evidence of deformation, often from the ridge crest until down to the toe, down to sea level, which can be up to 1,200 meters. They are creeping type movements, so they're usually moving at a constant rate and in the realm of anywhere from 2 to maybe 50 millimeters a year. So they're very minor slope movements. And we see deformation manifesting at the surface as geomorphic features following structural patterns that we call morphostructure. And these morphostructure are usually evidence of small failure surfaces developing within it, the larger slope. So we consider that the failure process is incremental and progressive. So as small failure surfaces develop and propagate, eventually will form a larger sliding surface where we can get failure of the entire slope. And failure of the slope, often these creeping slopes transform to rapid rock slope failures or landslides, such as rock avalanches, and depending on the environmental conditions, possibly debris flows as well or instead. They're gravitational, so there's not always an obvious trigger. But we worry about them because of past performance. So we know from examples, global examples around the world, that these creeping slopes do transform to rapid rock slope failures. And these are two examples. So on the left here, we see the Frank slide, which occurred in 1903 and killed somewhere between 70 and 90 people that were in the town of Frank below the mountain at the time. And on the right is Løren, the Løren disaster, which was a series of rock avalanches that occurred in Norway in 1905 and 1936. And respectively, they killed 61 and 74 people from impact of tsunami or displacement wave in the lake following the avalanche. So there are a lot of more recent examples, but I wanted to show you some dramatic images of what these can look like. So we know that they're a problem, and we know that we need to understand the hazard in order to live peacefully in these environments. So there's two key things here. We need to understand, or we need to gain knowledge of the subsurface conditions and what's happening at depth in terms of the structure and the failure mechanism to allow us to improve the hazard analysis. And to do that, we need to really, we base our understanding on one key thing, and that is that these slopes are deforming under gravity along structural templates. So anisotropic rock, and when I say anisotropic, I mean rock with a fabric or directionality or structure. We know from a huge array of literature that these structural templates in the rock mass control firstly the sliding surface. So we see often that the sliding surface of a rock slide, for example, actually follows foliation or joint surfaces, and the failure mechanism. So here on the right here is a study showing different types of rock failure mechanisms, which is defined by the structural environment of the rock mass. We also know that the structural templates control the surface deformation and the resultant slope morphology. So we see things like linear and elongate structures such as trenches, scarps, ridges, and open fractures, morphological depressions, and they typically will follow a pre-existing structure in the rock map. So we know that structure is controlling not only what's happening at depth, but it's also controlling how this deformation manifests at the surface too. So it's a really key way that we can gain more insight into how these very large slopes might be deforming. And it's obviously very important because oftentimes these slopes are so big that even if we put boreholes in them, we still wouldn't be able to gain a full understanding of what's actually happening. So to use this structural knowledge to gain understanding of the hazard potential, we need to look to the past. So the first key step is to study the regional geological history and gain a contextual understanding to your slope problem. And then the second step is mapping. So mapping, structural and geomorphic mapping to determine what structures you have present at your location and how these relate back to the first step in terms of the context. So what are the specific geological events which transpired to lead to the types of structures that you have at your site? Because these are going to tell you something about the characteristics of the structures in areas where you can't see them, such as at depth. And it also tells us a little bit about the conditions of the structures themselves. So then the third step is to ask yourself, what does step 1 and 2 give us in terms of our subsurface information, and how do we use that to interpret what might be happening? So I'm going to walk you through a case study here, and all the examples that I'm going to use are from this area of the map highlighted on the right there. Maybe I can turn a laser pointer on. Laser pointer. Yeah, here we go. So I'm looking here at the top of the Scandinavian peninsula and in northern Norway specifically. And so all the examples in geological context that I am about to give you comes from this specific area. So when we are looking at deforming slopes in the region, we actually consider the tectonic or geological events that are key to understanding the structures that we see today. And the first event is the formation of the bedrock that we see predominantly covering Norway, the Caledonian rocks. And these are the result of allochthonous thrusting of metamorphic naps. And so we find that in profile, the rocks actually are dipping to the northwest in a series of imbricated naps. So they're stacked and they're separated by thrusts. And typically on a local scale, we find that the fabric, so the foliation and folding and smaller scale thrusts typically dip with the larger nap structure. And in here you can see a cliff profile where we have 2 naps stacked, and you can actually follow the fabric of the rock quite nicely through the cliff profile here and see that it is generally dipping towards the northwest, and it's typically quite shallow. We also see, as a result of the snap thrusting and emplacement, that on a local scale we have sheared material, so ductile shear zones that contain very high-grade metamorphic minerals that couldn't have been obtained from crust level shearing events. So we know that they're old inherited shears, and they are likely zones of localized strain and possibly have been exacerbated by multiple phases of glacial loading and unloading, and then undergo current day weathering from groundwater flow channelization. The second important geological event is the opening of the Norwegian and the Barents Sea. So we had some large scale rifting. Today we have a passive margin, but at some point this entire coastline opened up. And we find that we have faults and clusters of faults which align generally perpendicular to the axis of the rifting. So it depends where you are on the margin, but typically we find, for example, fault orientations to the northwest, to the northeast, and to the north-northwest. And locally as well, we find that joint sets follow the same orientations. So they're likely related to the same tectonic events. So this is an example of, here you can see these discontinuities which zigzag in a sort of sawtooth pattern, and typically have a lot to do with the landscape development. And here you can see a series of normal faults which dip to the northwest quite steeply, and typically they offset the lithology, and we often see evidence of faulting from old fault gouge, for example, or lineations on the fault surface. So we know that they're inherited faults. We know that they're really old. The joints are typically very steep and quite planar and highly persistent. We also see in some places, and not commonly, but we do see exfoliation jointing likely related to the glacial history of the area. So these steep and persistent joints have a lot to do with the fluid flow through these unstable masses. Okay, so I'm going to present some specific examples now from the same region. And we've made some interpretations based on our structural and morphological investigations at the site, and considering this sort of structural context that I've just given you here. So the area that we're talking about actually contains a large cluster of unstable rock slopes. And you can actually go to the interactive map resource to see this, this database if you wish. So most of the deforming slopes are in metasedimentary rock, which is highly foliated. And commonly we find that these are mica schists or mica gneisses. The slopes aren't overly steep, but they probably dip between 20 to 40 degrees. And often these unstable slopes, they sit over fjords or river valleys, which increases the hazard potential due to the possibility for a displacement wave initiation or from landslide damming. And we have considered our rock slope deformations as biplanar, which essentially is a simplified way of saying that we believe there are sliding surfaces made up of multiple structures. So probably a stepped failure path. And you can see here on the left, this simplified diagram showing a rear rupture surface and a basal rupture surface. And at the base here, this sliding surface is actually controlled by foliation. So in order to present these slope deformations, we categorize them by which surface the rear detachment surface of the slope failure actually follows. So in the case where we have moderate to steep foliation dipping with the slope, and it doesn't occur very commonly, as I said before, the fabric is generally quite shallow in this area. But where we do have it, we find that we can get sliding on the foliation plane. So sliding initiates on the foliation plane, and we've called that foliation plane rear rupture. In cases where we have a shallow dip, or possibly the dip is into the slope or unfavorable somehow, we find that the deformations detach from the mountain using a different surface. So often this is the joint plane, but it can also be a fault plane as well. So I'm going to now present some actual examples of these. This is Normandale-Stinden, and I apologize for the messy aerial. But this is an example of a foliation plane rear rupture. Okay, so here we have the slope deformation. And you can see this is a photo from the crown of this, or the head of the slope. And here we actually have foliation, which is dipping quite steeply. It's around 35 degrees towards the fjord. And we have a series of slabs that have essentially detached from the mountain, and the material is sliding on these foliation surfaces. So you can see here at the head, these nice smooth sliding surfaces. And we see at the toe that we have a cliff, and we find that we have seepage or a groundwater springs around the toe line of this slope deformation around here. And we have typically marshy ground or boggy ground and plants that grow in that sort of terrain. Sorry, I'm frozen. Just give me a minute. Okay, sorry, I have to restart the PowerPoint. I'll be right back with you.
Louise, we're just looking, okay, now we're in the beginning, so move accordingly.
Sorry.
No worries, don't worry.
Okay. Okay, we're back. Sorry about that. Yeah, okay, so this is Normandale-Stinden again, and this is our interpretation of the site. So here you can see let's get the laser pointer again. Here you can see our slabs of sliding rock on the foliation plane, and the toe here at the base with the seepage point. And we have generalized the sliding plane, but we think that is a combination of foliation and possibly step fractures on some lower angled surfaces. We can't see a lot at the surface, and we've made some pretty big interpretations, and these are based on structural mapping in situ areas and also morphostructural mapping in the dislocated areas. This slope is called Varas, and this is an example of a joint controlled slope deformation. So here you can see this really nice opening at the head of the unstable slope here. The head scarp here, it follows a combination of different joint surfaces. And we have a huge amount of downward movement. So something like 80 meters of downward dislocation there along this back scarp. And as the material sort of moves forward, we get these really nice corresponding counter scarps here, which also follow the same joint systems. On the top, we actually have a lake system here. So in late spring and summer after snowmelt, we find that these fractures actually fill up with water. And over the course of the summer, as ice within the slope begins to melt, fluid can flow through the slope. And we see seepage at the toe here again. In our interpretation of this slide, here you can see we have this opening here and a small graben where material is dropped down between the opening surfaces there. And as I said, there's probably some complex hydromechanical control on the slide that we don't quite understand. But there is a filtering of water from the lake above and to the toe at the base here. And again, we've generalized the failure path, but we believe that it is comprised of steep joints at the head, and then a combination of possibly joints and possibly foliation planes at the base. And the last example I'm going to give you, this is Laxvattenfjella, and it is what we're calling fault controlled. So this site is a little tricky because the top of the mountain actually follows an inherited normal fault. So we know that it's a fault because the gouge material has been dated and it's quite old, to the Ordovician, I think. But it also has a second splay here. And the second splay is what defines the upper limit of the unstable material. So again, some really nice morphostructure. So you can see here at the top, we have a series of slabs, sliding slabs, creating these really nice counter scarps in series. And these are just below the very steep fault surface. We also find that within these slabs, we have these thin veins almost of philitic material, which probably act considerably to lower the shear strength of these sliding surfaces. And we also see some back rotation here. So we see some really nice terraces which have rotated backwards and sitting against the slope now. And here you can see some of the gouge exposed. So there's up to about 0.5 meter of fault gouge, and we see crisscrossing fiber lineations as well. And as I say, the slope is quite complicated. So we've done our best to interpret it, but it is a work in progress. we see the foliation is quite shallow above the headscarp, but actually immediately below the headscarp or the fault plane, we have very steep sliding surfaces controlling these slabs that I showed you on the previous slide. So either we have a fold axis here, or we have an overturning of the unstable material and collapse. So within this study, we actually looked at 9 different deforming slopes and made some observations about the geotechnical characteristics of these slides. So one of the really key factors is that what we assume is the basal sliding surface is actually is on a very low, dipping at a very low angle, and technically we shouldn't be seeing any sliding on these angles. But we have a huge amount of material that has dislocated at the upper end of the slope. So we have to assume that the force from this upper wedge of material is allowing for a sliding on the basal rupture surface. And of course, the groundwater interaction probably has something to do with it as well. This is a generalized schematic that we came up with to represent our foliation controlled slope deformations. So here you can see sort of series of slabs and often quite a gentle undulating surface. And at the base, we often see but not always, we often see a buckle or a bulge in the lower surface and a seepage point here as well. And that's our only indication that we actually have a toe, to be honest. So we see typically features of extension at the top and compression at the toe or at the lower end of the slope. And we have to assume that there is some transfer of load in the middle there. This is our interpretation of those types of slides. And in the same vein, we've also created a schematic for our joint and fault controlled slope deformations. And here we have often a steeper implied basal sliding surface, and not hugely steeper, but somewhat steeper. And we assume that the same effect of load transfer is allowing for sliding on these lower angled surfaces. And typically these sites are on steeper slopes, and obviously where the foliation is too shallow for a detachment at the upper surface. And we see often a sort of stepped morphology at the top, and some evidence of compression at the toe. And sometimes we see a buckle or a bulge as well. If you want to read more about the study, you can see the paper here, which goes into it in a lot more detail with a lot more examples. But I just want to conclude by saying that knowledge of the structural environment informs our subsurface understanding. And this is really important in sites where mapping or boreholes of the subsurface conditions are not feasible. So we really have to understand what is happening at the surface, put it in a wider context, and make some interpretations about what might be happening at the subsurface. And these structural categories within this framework helped us to discuss different failure mechanisms in large slope deformations, but they are very much a localized classification and maybe don't apply to other geological environments. So we haven't proposed this as a new scheme for classifying slope deformations, but more for a way to present what we see as happening. So yeah, thank you for listening to me, some of the references that I used here. And you're welcome to contact me at my institute, or you can follow me on Twitter here and at my handle, which is Landslide Louise. Thank you very much.
Thank you very much, Dr. Louise. Are there any questions? We have some time ahead, so if there are any potential questions Dr. Vick could answer, please provide them in the text in the chat section. So let's wait for that. I don't know if Professor Marinos is back. Okay. Just to start the conversation, Louise, can I ask you, are there any, did you think probably provide some, let's say, causes in the area or some boreholes?
Some what, sorry?
Some boreholes. Did you have the chance to have some boreholes in the area?
Yeah, so actually there has been drilled some boreholes in the past by the authority responsible for monitoring these high-risk rock slope sites. Well, one in the field area actually. But it's very challenging because the mountains are very big. And in order to actually set up a drill rig on the mountain, it involves helicopter transportation and some way to pump water up, you know, anywhere from 500 to 1,200 meters from sea level. So it's a huge cost and a huge practical challenge. So
Yeah.
that is actually why we have been making these sort of fantastical interpretations, because it's really our only option.
It's an excellent work, I could say.
Thanks.
So I don't see any questions for now. So we have one from Sarah. Are there also large-scale deformations in igneous rock masses? Examples you have shown are in metamorphic and sedimentary rock masses.
Yeah, that's a good question. So, of course, we do see that, but in my part of the world, not so much. So we don't have any primary igneous rocks. Everything is highly metamorphic. And in the sort of meta-volcanic rocks, we don't see a lot of slope deformation. And it could be that they're less anisotropic, essentially.
So are there any questions once more, both for our presenters, Dr. Marinos and Dr. Vick? If there are any questions, we have 5 to 10 minutes more. So we have one question from Ishak from Malaysia. The question is, what are your opinion regarding effect of the rainfall toward the rock slope failure?
Yes, that's also a really good question. So, oh, sorry, was that for me or Vassilis?
I think you can both answer if there is something on that.
Yeah, well, yeah, it's kind of a two-part question. So there's been a lot of work to look at the temporal behavior of these slopes in Norway, and we don't actually see any kind of cluster of failures in time periods where we expect that there was probably more rainfall in terms of paleoclimate. However, in the greater Europe, we definitely see that. And on a kind of a smaller current day scale, because several of these slopes are quite well instrumented and monitored in real time, we do see slope movements in response to rainfall. And there is a lag time, of course, and it depends on the geological environment of the slope. But probably one of the biggest factors here is snowmelt, because we're in the Arctic and we have 8 months of snow, and then we don't really have a spring. We tend to go from winter to summer in one day, and then we often get a huge amount of snowmelt and a lot of water being flushed into these highly fractured slopes. So there is a strong hydromechanical control on these slopes, but we don't quite understand it yet. So it's a work in progress.
And that's something interesting. Also, I don't know if Professor Marinos would like to add something on that, depending on the rainfall regarding the cases.
No, I don't have anything to add into that. But rock mass characterization, it's one thing, but definitely to monitor the groundwater is of great importance in slope stability. So this is a totally another subject that needs to be very, very carefully analyzed, because it's one of the primary triggering factors of the slope instabilities. So this is a very general question. I mean, every case, depending on the site-specific and the geological particularities and permeability of the materials and how these are drained, this is every case is particular. So, but definitely this is something that you should take care when designing or analyzing slope stability.
Definitely, rainfall is a really crucial point. So I don't see any further questions from the attendees. Just one came right now from Rochelle Taylor. There's a lot of work being done on the subject of precipitation and slope failure on the Mamtor landslide, Derbyshire in UK, by Anisotropic and Sam Green. Probably, yeah, I don't know that. I don't know, some of the presenters know something on that, but there are a lot of studies. Yeah, there are a lot of studies providing thresholds depending on the events. And so this field that more work has to be done, definitely. So by ending this first webinar series, I would like to both thank you for being our initial speakers for the first e-YEG day. I think a lot of really find that it was a really informative tool, depending on the overall situation. I will have to say that there are more webinar series gonna happen each month, and some more actions from the following months. Once again, I would like to thank you, Professor Marinos. I would like to thank Vick, Professor Vick, Wyatt, and all of the attendees being in the current session. Goodbye, on behalf of the e-YEG committee. Thank you.
Thank you very much.
Thank you for cheering, Stratis.
Yeah.
Thank you.
Okay.